Let's start by looking at an example. In this video, I'm going to introduce you to the idea of the buoyant force. The buoyant force is the net force exerted on an object immersed in a fluid by the pressure of the surrounding fluid. To begin, let's look at an example. In this figure, I've drawn a container which is completely filled with a liquid with a constant density. The idea here is that this is the upward direction, and then this is the downward direction. Somehow, I have stuck a solid cylinder into this container, which is otherwise filled with the liquid. Let's start by going into the figure and illustrating the action of the liquid pressure onto the cylinder. What I like to do in these figures is draw little squiggly arrows to illustrate how pressure is pushing on the solid object. A couple of things to keep in mind here is that, first of all, pressure is going to become greater as we go deeper into the liquid. And also, the push of the pressure on the solid is always going to be perpendicular to the surface of the solid. So at the top surface here, I have the weakest pressure pushing down on that top face of the cylinder. But as I go deeper into the liquid, the pressure is going to get stronger, and I illustrate that with longer squiggly arrows. Again, notice that everywhere I draw those squiggly arrows are pushing perpendicular to the surface of the cylinder to illustrate the action of the pressure pushing perpendicular to the face of the cylinder. Now let's go down the other side of the cylinder. And again, the action of pressure on this other side of the cylinder will be perpendicular to the face of the cylinder. And also the strength of that pressure increases the deeper I go into the cylinder. And then the strongest pressure in the figure is going to be pushing upward on the bottom of the cylinder. Now, if you look at that pressure, you can see, as we would expect, the weakest pressure pushing down on the top surface of the cylinder, and the strongest pressure pushing up on the bottom surface of the cylinder. Let's say that pressure at the top surface is P sub T, and let's say that the pressure at the bottom surface is P sub B. Now, suppose that we wanted to determine the net force that the surrounding fluid pressure exerts on this cylinder. Now, it would help to know the area of that circular face of the cylinder up here, and then it would be the same area down here. Can you tell that the net force that the fluid pressure exerts on this curved surface of the cylinder is zero, right? We have as much pressure force over here pushing to the right as we do pressure force over here pushing to the left. So the net force exerted by the pressure here combined with the pressure here will be zero. On the other hand, let's think about the forces exerted by pressure downward on the top surface and upward on the bottom surface. At the top surface, let's say that the net force from the pressure on that top surface is F sub T for top. We know that the strength of that force would be pressure times area. So let's put in as the magnitude of that force, pressure top times area. Then the net force from fluid pressure pushing up on that bottom surface, let's call that F sub B for bottom. And the magnitude of that force would be the pressure at the bottom surface multiplied by the area. Because this is a cylinder, the area of that top surface and the area of that bottom surface would be the same. What then would be the buoyant force, or in other words, the net force that the fluid pressure exerts on the cylinder? Well, that buoyant force would be the vector sum of the force on top and the force on the bottom. Now, since that force on the bottom is stronger, can you see that the net force would be up? So our buoyancy force, the net force exerted by the surrounding fluid pressure, would be up. Now, what would be the magnitude of the buoyant force? Well, the buoyant force is a combination of a stronger upward force and a weaker downward force. So the magnitude of the buoyant force is going to be the difference between the strength of that upward force and the strength of that downward force. In other words, the buoyant force is pressure bottom times area minus pressure top times area. And now we have worked out an expression for the buoyant force on the cylinder completely immersed in the liquid. Now, getting to this expression wasn't really so bad, but what would we do if we had a more complicated shape than this cylinder? If the shape was more complicated, it could be much harder to get to an expression which correctly gave us the buoyant force. So in the next video, we're going to see how we can still find an expression for the buoyancy force acting on an object immersed in a fluid, even when that object has a more complicated shape than the cylinder we've been studying here.